We'll get started. Okay. All right. So today I have this titled "Review of Statistical Inference." Okay. So I'm assuming you're all stats majors, or maybe at least interested in stats minors or something. But not everyone took Stats 10 here at UCLA. Some of you guys took AP Stats in high school. Some of you guys went to a community college and took stats class there or something. So I don't know your stats background. And in the past, students would come to office hours, and I realized that they were missing certain fundamental concepts from introductory statistics. So I just wanted to spend a lecture going over some of these things. You know, if today is totally review for everything, then great. Then you know exactly what you need to know. And if any of the stuff today feels new, or you go, oh, I never thought of it that way, then great. I'm glad we did today's lecture then. So that's what we'll do. Okay. And I'll just throw in bits and pieces here. Okay. So we're going to review intro stats. Okay. So probably the first thing you guys were exposed to in stats were the mean and the median. Okay. And most classes will cover like how do you calculate the mean. You add them up and you divide by n. Or the median, and you start by the ends and you sort them in least to greatest, and you kind of work your way in and you say, okay, this value is the median. I'm not sure if people ever explained the concepts behind the median. They're both measures of center, and what the median does is it balances the number of points that are above or below the median, okay? And then the mean balances the deviations that are above or below or higher or lower of the points, the deviations of the points, okay? And so because the mean kind of takes into account the deviation or the distance from the mean, it's going to get pulled into the direction of the skew, okay? So they probably covered that if you have data that's skewed right, your mean is going to be greater than your median in general, things like that. So here's like a little picture. Here I've got these 6 data points, 1, 2, 3, 4, 10, and 10, okay? And the median is in blue, okay? I've got the points 1, 2, 3, 4, 10, and 10, and the median just balances these. So I've got 3 on the left, 3 on the right, and the median doesn't care that these points over here are like super far away. It doesn't care if they're like way over here or over here. As long as it's above the median's happy. The median's going to stay put right here, okay? So I've got 3 above, 3 below for the median, okay? If we think of the mean is that, I add these up and I divide by 6 and I get 5 as the mean. And here I look at the deviations, okay? So this point, which is 4, is 1 unit below the mean, so it has a deviation of -1. 3 has a deviation of -2. 2 has a deviation of -3, and 1 has a deviation of -4. So the deviations of the points below the mean add up to -10. We look at these 2 points which are above the mean, 10 and 10, they both have a deviation of +5, +5, okay? And those deviations add up to +10, okay? And so the mean balances the deviations. We got 10 below, 10 above for the deviations, and that's the mean. So it's rather a remarkable fact that just adding up the numbers and dividing by how many you have achieves this task of finding the location that balances the deviations above and below. Okay, but that's what we have. Okay, so that's the mean. We have the variance. Okay, the variance is you can think quote unquote the average squared distance from the mean. So we take each of these deviations, okay, and we square them, and then we take the average, right? Technically, it's not the average because we don't take those squared deviations and divide by n. We divide by n-1, okay? And then the standard deviation is the square root of the variance, okay? Larger values of variance and standard deviation mean that the data is more spread out. smaller values of variance and standard deviation mean the values are closer together, okay? All right, you guys all took 100B, or you're taking it now and wrapping it up, or I don't know. So you had to, so for the variance, you added up the squared deviations and you divide by n minus 1, right? And you had to prove like why n minus 1 is a value to use to make it an unbiased estimator of the population variance or something. Can anyone provide maybe an intuitive reason why we use n minus 1 versus n? Because okay, yeah, well, so yeah, well, but why would n minus 1 make it unbiased, or why would dividing by n? So if I take, like, if I just took this, right, and I took my deviations, 5 squared plus 5 squared plus 1 squared, 2 squared, 3 squared, 4 squared, and if I added them up, I have 6 squared deviations, and if I add those up and divide by 6, my variance is going to be biased, right? Why is it going to be biased? Why would dividing by n minus 1 make it unbiased? No? Okay. So the reason is when we are talking about the population variance, we are measuring the squared distance from what value? From the population mean, right? So we want to know what's the average squared distance from the population mean, okay? Do I know the population mean? I don't, right? So I'm using, instead of the population mean, I'm using my sample mean, okay? And so because I'm using my sample mean, the sample mean is always going to be in the middle of your own sample, right? And so the population mean might be a little bit higher, it might be a little bit lower, okay? And so if I used any other value other than my sample mean, my deviations would end up being bigger, okay? And so if I use the population mean, it might be over here, and my deviations might be a different value, and my total squared deviations would be a little bit bigger, okay? And so the fact that I'm using my samples mean to calculate the deviations mean my average deviation is going to be a little bit lower than what it should be because the population mean is actually somewhere else, right? And so it turns out that n minus 1 is the exact correction that we need to use to compensate for that difference. I don't know. Does that kind of make sense? The difference between why we're dividing by n minus 1. Okay, anyway, you guys proved that in 100B. Okay, and then now we have the normal distribution. Normal distribution is unimodal and symmetric, and the basic idea is if something follows the normal distribution, most of the values are near the middle, okay? Most of the values are somewhere in here, and only rarely do we get values above 3 or below -3, right? And so the empirical rule, I'm missing my approximate sign, but approximately 68% is within 1 standard deviation of the mean, about 95% is within 2 or 1.96 standard deviations of the mean, and almost all 99.7s within 3 standard deviations of the mean. So that's, you guys have these 3 numbers memorized, right, for your empirical rule? So every statistician, when you graduate, these are numbers you should have memorized. I feel like I should have a list of things every statistician who graduates should know, not so they don't bring shame to the UCLA stats program or something, you know. All right, let's talk about populations and samples. All right, so every research question has an associated population, okay? And the population is everyone who is relevant to answering the research question, okay? Population is too big to be studied directly, all right? And we might not even know how to identify everyone in the population, right? So, example, you might have a research question, is this experimental drug, XYZ, is this effective at treating disease JKL? So you've got some mystery disease, and you want to know, is this experimental drug effective at treating it, right? And so the population would be everyone who has this disease, okay? But who has the disease? That's a difficult population to track down, right? We don't even know, right? That's part of the problem. Coronavirus and stuff, like we don't even know who's sick. Okay, this is a thing. So finding out the population is hard, and so or in the United States we do a census once every 10 years, and it is a giant undertaking, right? Yeah, they have to hire a whole bunch of people just to count how many people there are, and even then the count is not 100% accurate because we get people who are actively trying to avoid being counted and stuff, and the people who just are kind of in situations where they're difficult to track down, people who don't have permanent addresses and things like that. And so counting how many people exist is not easy. Okay, so populations are hard, and so what we do in statistics is that we select individuals from the population to be part of our sample, right? And the idea is that we study the sample. Based on what we see in the sample, we make conclusions about the population. So this population is supposed to be this big, large entity, too big for direct study, and we're just selecting individuals from it, right? So ideally, the samples that you select, the people that you select from the population are representative of the population, okay? One method that should produce representative samples is random sampling, but that's actually hard to do, right? And random sampling itself is not guaranteed to produce representative samples, okay? So, ideally we get representative samples, and we might do random sampling, but it's not even guaranteed to produce representative samples. As part of our curriculum, we don't make you take a course on sampling. I don't even know if there is a course on sampling for the undergraduate level, but it's difficult. Like if I told you to get a random sample of students at UCLA, what would you do? Is it even possible? Maybe. I mean, so if you try any method where you're like interacting with, like if you stand on Bruin Walk and you try to talk to, that's definitely not going to be random, right? Because you're only going to get people who walk on Bruin Walk, which is not going to be people who stay at home, right? Only people who like go to campus and go to class, and choose to walk down Bruin Walk, right? And some people actively avoid Bruin Walk and stuff. Maybe the university can give you an active student roster, right? And you'd probably have to show that you need this or something. But it's really hard, right? And if we said get a random sample of people in the city of Los Angeles, that's like, I have no idea how you're going to do this, right? So there's organizations that dedicate all of their efforts and energy to try to get representative samples because it's important, right? So right now it's like election season, and people want to know like which candidate's going to win and who's going to be the nominee and stuff like that. And so different organizations conduct surveys, but these surveys aren't going to mean anything if the people that they select aren't representative of the population, right? And so this is a difficult thing, right? So one thing that people sometimes do is just randomly dial phone number digits in the hope they get someone to answer. It's hard, okay? I guess I wanted to talk a little bit about. Have you guys taken 101B yet? No, any of you? No one? Some of you. Okay. So in 101B, probably you will have to do a project called the island. I don't know, do you have to do the island project? Okay. So you do this, it's a design of experiments, and to kind of simulate the doing an experiment. Doing like a real life experiment is like super costly and super expensive. So the island is like a simulation where you can do experiments for free and stuff. But part of the, I don't know if you experienced this, but when you were working with the island, I think they purposely made it impossible to get a random sample of participants, right? I don't know if you did that, right? You had to like go to each island, talk to the city hall, and find a list of people. And they made it really hard to get a random sample because it's in real life, it's really hard to get a random sample, okay? But anyway, I don't know if you enjoyed the island experiment, but I think it's pretty neat. For those of you who are going to take 101B, I just want to give you kind of like the big picture idea and reason behind 101B is that I'd say there's kind of two faces to statistics right now, okay? And this is oversimplification, okay? But so the 102 series is the computational methods, and the computational methods kind of focus on, are often used in situations where you have just a massive amount of data, okay? So any kind of computer-generated stuff, text stuff, you got all of these internet logs, you got thousands and thousands and thousands of entries in, and we're just trying to extract nuggets of information from all of the data. And so we focus on methods that look at big samples and how to cluster and reduce dimensions and stuff like that. Okay. The other application of statistics is in kind of lab settings where obtaining data is very costly, and every observation you have is very represents a lot of effort to obtain. So if you think of a medical trial where you're doing some kind of testing out medicine, every observation you obtain, each person who participates, you can imagine costs thousands of dollars. Okay, so let's say there's you're testing out some cancer drug. Okay, so first of all, you need to find a patient who's willing to consent to be part of the experiment. Then you need doctors and nurses who are trained in the administering of this experimental medicine. You need the manufacturing of the medicine itself, and you probably need multiple observations recorded for each patient. So each patient costs, the data for one patient costs thousands of dollars. And so you'd be lucky if you get like 30 or 40 observations. Okay, that might be the representation of $50,000 of resources just to get 30 or 40 data points. Okay, and so you don't want to waste any of that data. And so 101B, the whole idea behind that class is how do you set up your experiment in the first place so that when you go out and collect data, you can be as efficient as possible with the information you're collecting, right? So in the island, when you conduct an experiment, you just click a button, but they intentionally, I think they put a timer where you have to wait like 5 minutes before you get your results or something, okay? And it's a little bit frustrating, but that just represents just a tiny amount of the actual work that goes into collecting real data, right? So they don't want you to just say like, oh, I'm going to collect data from 1,000 people, because that's unrealistic, right? So more realistic scenario is you're going to collect data from maybe 40, 50 people, and each of those things take a little bit of time or a lot of energy. And so in the island, you maybe have to wait 5 minutes to get the results of one experiment, whereas in real life, it's a lot more. So you want to design your experiment so that you can extract the most information out of a small set of data. And so that's what 101B is all about. And I really like that class. But I also love these classes, all of these computational things. This is where I feel most comfortable, but I do enjoy the 101 series as well. Okay, anyway, talking about samples, when you take a random sample of data from the population, you might often calculate a summary statistic like the mean of the sample, okay? And because the sampling process is random, if we were to take another random sample, we would get different values and we would get a different sample mean, okay? And so the question is, what kind of values can we get for the mean of a sample? Obviously some values are going to be more likely, some values are less likely. And so the distribution of all the possible values of the sample mean from all possible random samples is known as the sampling distribution of the mean, right? Sampling distribution. So I hope you guys remember this concept, the sampling distribution of a statistic. And so we create a sampling distribution via simulation. So we can do this, and you start off with just some population that you hypothesize. So here I said, let's start off with the standard normal. We're going to say, let's pretend that the population is normal, has a mean of 0, standard deviation of 1, okay? And then what I do is I'm going to draw a random sample from the population and calculate the mean of that sample. Okay, then I do it again. I draw a different random sample, calculate the mean of that different sample. And I do this many times, and every time I record the sample mean for each random sample. And then what we're going to do is we're going to look at the distribution of all the different sample means that we've produced, right? All right, and then and so when you're looking at the sampling distribution of the mean, the central limit theorem kicks in, which says that if the sample size is large enough, then the sampling distribution of the mean will be normal, and it's going to have a mean equal to the population mean with a standard deviation sigma over the square root of n, right? So here's just this. This curve represents the population. The population is a standard normal. These red dots down here, or these lines, ticks, is the rug plot. These are the 16 data points that I got in this random sample, and the mean of these 16 points is a little bit lower than 0. Okay. Here's another random sample, and the mean of these 16 points is over here. Another random sample, the mean of those 16 points is here. Another random sample. In each of these, we're calculating different means. Okay. And every time we do this, okay? And so I've done this, so here's my code. I do this 10,000 times. Every single time, I draw 16 values from the standard normal, and I call that my sample. I calculate the mean of my sample, and I record that in sample means. So I'm going to get 10,000 different values of sample means. And the mean of all of those sample means is something very close to 0. And the standard deviation is something very close to 1/4, which is 1 over the square root of 16. Okay, so this is exactly what I expect. Here's what the sampling distribution looks like. This is just a histogram of it. Okay, it looks normal, and we can see that nearly all of our data, all of our sample means are between -0.75 and +0.75. Okay, whereas the original standard normal, you have to go out to -3 and +3 to get almost everybody. Here we go out to -0.75 and +0.75, indicating a lot less spread. Okay, QQ plot shows that the sampling distribution is also normal. Okay, and so here's kind of the key takeaways is that the central limit theorem establishes that the mean of a random sample comes from the normal distribution centered at mu, that is the population mean, with a standard deviation of sigma over the square root of n. Okay, and then the empirical rule tells us that 95% of the time, a random value drawn from a normal distribution will be within 2 standard deviations of the mean. Okay, so this is what I can say. When I draw a random sample, there's a 95% probability that the mean of the random sample, that is 95% probability that x bar is within 2 standard deviations of the population mean mu. Okay, 95% probability that x bar is within 2 standard deviations of mu. Okay, so With that, I can flip it around and say when I do observe a random sample with mean x bar, I'm 95% confident that the population mean mu is within 2 standard deviations, that each standard deviation being sigma over the square root of n, 2 standard deviations of x bar, okay? So I'm 95% confident that mu is within 2 standard deviations of x bar, okay? And that forms the foundation of a confidence interval, all right? Except with a confidence interval, what's the issue? The issue is that we don't know what sigma over the square root of n is, okay? We don't know the exact standard deviation of the population. So what do? We use the standard deviation of the sample. We use S as a guess for sigma, okay? So that makes sense, all right? But using S instead of sigma introduces extra uncertainty, so we compensate for that by using the t distribution rather than the normal distribution, and thus your confidence interval looks like this, okay? X bar plus or minus t times the standard error, S over the square root of n. Okay, on this page I say I'm 95% confident that mu is within 2 standard deviations of x bar, but over here I can say there's a 95% probability that x bar, the mean of the sample, is within 2 standard deviations of mu, the population mean. Okay, so why can I say 95, this is at least from a frequentist perspective, why am I allowed to say 95% probability that x bar is within 2 standard deviations of mu here, but I'm not allowed to say that over here. Here I say I'm 95% confident that mu is within 2 standard deviations of x bar. So why do I say confident over here, but I can say probability over here? Anybody? Yeah.
Isn't like the confidence interval thing that the probability of something being in the interval is 1 or 0 because like it's already in there. So when you interpret a confidence interval, you don't use probability because like you're looking at a certain number of samples.
Right. So you're getting at this notion of that this value mu is either in the interval or it's not, right? Okay. So I have a little bit of an analogy here. Okay. So here I've got a coin, and it's a quarter. So, I'm going to flip the coin, and so I'll ask you, before I flip the coin, what is the probability that the coin will land heads? Okay, not a trick question. You tell me it's 0.5, right? What's the probability that the coin will land heads? You say 0.5. Okay, so failed. Okay. Of course, it rolled underneath the thing. It's pathetic. Okay, all right. So here's the coin. I flip it. All right. So now I have flipped the coin, and I ask, what is the probability that the coin has landed heads? Okay. So maybe you're saying 0.5 or 0.1. Okay. And then I look at it. Okay. And then I cover it back up, and I ask, what is the probability that the coin has landed heads? Okay, and you're now weirded out by this series of questions, right? So some of you are saying 0.5, some of you are saying 0 or 1. And the truth is after I flipped the coin, the question is a nonsense question, okay? That probability only exists for events with uncertain outcomes, okay? So once the coin has landed, it no longer makes sense to ask what is the probability that the coin has landed heads, because it either did or it didn't. Okay, there's no uncertainty anymore. The coin either landed heads or it didn't. So the question, what is the probability that this thing that happened in the past has happened, is a nonsense question, right? You don't know how the coin landed, so you can say I am 50% confident that it landed heads, okay? But it doesn't make sense to talk about a probability of an event that already happened, okay? So it landed heads, by the way. So that's what we've got going on here, okay? The value of the population mean mu is a fixed value, okay? At least from a frequentist perspective, okay? Bayesian statistics probability is different. But from the frequentist perspective, the the value mu is treated as fixed, and there's no uncertainty about it. It's some number. If we were able to freeze time, measure everybody in the population, we could get the exact value of the mean mu, okay? That would be the true average of everybody in the population. It's a fixed value. There's no uncertainty about it. But we don't know what it is, so we can talk about there being some confidence, but there's no probability associated with that. Okay, anyway, the other statistical inference tool that you learned is hypothesis testing, right? And so in hypothesis testing, we imagine a hypothetical population with a hypothetical mean and standard deviation. And what we do is we perform calculations to see if this hypothesized population could produce the observed sample that I actually have, right? So that's the idea behind a hypothesis test. So, the two independent sample t-test takes samples from two populations and tests to see if the respective populations have the same mean or not, right? So you've got sample 1, sample 2. Sample 1 came from population 1, sample 2 came from population 2, and the question is, does population 1 and population 2, do they have the same mean or are they different means, okay? So the null hypothesis, all right, in this case would be that there's no significant difference between specified populations, right? And that any difference that we observe, that's just due to random sampling, okay? Or measurement error, okay? And then the p-value, so this is a definition that every graduate of statistics needs to know, right? Is the p-value is the probability of obtaining a result equal to or more extreme than what was actually observed if we assume that the null hypothesis is true. So if the null hypothesis is true, what's the probability of getting our observed data? All right, so we, for this case, we would do a t-test, and what we would do is our hypothesis, our null hypothesis says that the two populations, okay, the population that produced sample 1 and the population that produced sample 2, those two populations have the same mean, okay? And so if those two populations have the same mean, when I take a random sample over here and a random sample over here, I expect my two samples to have very similar sample means. I would expect x bar 1, x bar 2, I would expect those two values to be around the same, okay? Or I would expect them to have a difference of 0, okay? But of course, because of random sampling, they're probably not going to be exactly equal to each other, and that difference is not going to be exactly 0. And so the question is the difference I get, is that significant, right? And we answer that by finding the p-value. And that's the answer to this question. If the two populations truly were equal, then what's the probability that this random sample and this random sample have a difference of whatever we observe, okay? So just to put some numbers here, our null hypothesis would be that mu1 and mu2 are equal. And let's say sample 1 has a mean of 10, sample 2 has a mean of 12, okay? So I have an observed difference of 2 points, okay? Is that observed difference of 2, is that significant, right? And we can't answer it without more information, okay? And so it all depends on how big the standard error is, right? What our sampling distribution, how much standard error exists in the sampling distribution, right? And so the standard error, one scenario is that the standard error is very small. And so the observed difference of 2, maybe that's like 5 times bigger than the standard error, okay? So in that case, this difference of 2 is significant, okay? On the other hand, the standard error could come back, like when you look at it, that the standard error is big, and so this difference of 2 points is not that big. It's maybe only 1.2 times the standard error, okay? And in that case, the difference is not significant. So you know, we have to do this, right? So, and rather than just saying that our difference is large or small compared to the standard error, we can calculate a p-value, right? So the p-value is the probability of observing our data or something more extreme. when the null hypothesis is true. So if our p-value is small, then that means that our observed difference of 2 is really unlikely to happen if the only source of variation is random chance, okay? So most of the time random chance should produce values close to 0, and we're getting a difference of 2, that's really unlikely to happen. So because we did actually get this difference of 2, we can be pretty confident that our data is not the result of just random sampling alone. Okay, and so we reject the null hypothesis. We say the two populations have different means. Okay, or on the other hand, if the p-value comes back large, it says, yeah, you got a difference of 2 points. You're expecting a difference of 0, but random sampling shows that you can get quite a few different differences, and getting a difference of 2 is not that unusual. Okay, and therefore, this doesn't prove that the null hypothesis is right, but at the same time, we can't eliminate the possibility that this difference of 2 was just a result of randomness, okay? So we say, I will not reject the null hypothesis, and I'm not ready to conclude that the two populations have different means, okay? And so this is kind of where we go, right? All of these things are what we call parametric hypotheses tests, okay? They're parametric because they rely on the central limit theorem, and the central limit theorem uses the normal and t-distribution, and those are parameterized distributions. They have parameters like the mean, like the standard deviation, and the degrees of freedom, and they have kind of underlying mathematical ideas, right? And you have to prove these in 100B and stuff like that. And so you have to check to make sure you're checking the conditions, okay? And what we're going to do next week is we're going to look at some randomization tests, okay? And in a randomization test, the null hypothesis is going to be that there's no difference between the group means. It doesn't depend on the central limit theorem, but just the randomization process itself, okay? And it depends on this idea of exchangeability, which I'll talk about next week, okay? But before we do that, we have to talk a little bit about data collection, because the process of data collection will has implications on what kind of tests I can conduct, whether it's a randomization test or a bootstrap test or something like that, okay? All right, and so this is just some silly scenario where a dentist wants to know if taking a daily dose of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C. Okay, so canker sores are, little sores in your mouth. Does taking vitamin C reduce that? Yes or no? Okay. All right, and so we're going to look at 4 scenarios, and it's going to be a little bit repetitive, but we'll talk about this, okay? So first, the dentist convinces all the dental patients in town with appointments in the first 2 weeks in December to be subjects of a study, right? And then we divide them into 2 groups, those who take 500 milligrams of vitamin C each day and those who don't, right? So, and then we ask if they have canker sores in their mouth. We check their dental records to see if they complain of canker sores. We compare the proportion of those who take vitamin C and have canker sores with the proportion of those who don't take vitamin C and have canker sores. And then maybe we find a significant difference between these 2 proportions, okay? With those taking vitamin C having fewer canker sores. All right, so what can we conclude from here, right? So first question, is this a random sample? Okay, it's not a random sample, okay? And is this an experiment or an observational study? Okay, so the answers are it is not a random sample and it is an observational study, okay? It's not a random sample because we just looked at the people first 2 weeks of December, and so that's not random, okay? It's an observational study because we did not assign treatments. We just asked them, do you take vitamin C or not, okay? And so the people, through, by their own choice, either do or do not take vitamin C. And so maybe those who do take vitamin C also, if you're the type of person who takes a multivitamin, maybe you're also more likely to practice other healthy practices, right? Versus, other people. I don't know, okay? And so basically, we cannot because it's not a random sample, we cannot generalize to a larger population. And because it's an observational study, we cannot draw a cause and effect conclusion. So all we can say is that for these patients, those who take vitamin C have fewer canker sores than those who don't. We cannot attribute the cause. We don't know why. And we don't know if this result would be consistent with another group. Okay. All right. So over here, still we're dealing with patients with in the first 2 weeks in December, but then we do random assignment. Okay. We randomly assign and say, you guys take vitamin C, and then the other half, you do not take vitamin C. Okay. We do the study. We come back with a difference. Okay. What can we conclude? All right. So here, it's not a random sample, so we cannot generalize to the greater population, okay? But because the treatments were randomly assigned, okay, the difference that we observe can be attributed to the vitamin C, okay? So we can draw a cause and effect conclusion because this is an experiment and we did the random assignment, all right? But we can't generalize to other groups. But we can say for this group, we do believe we know why. And it's the vitamin C that's making the difference. Okay. All right, over here, random sample observational study. Okay. So we somehow get a random sample of dental patients in the town, convince them to be part of the study. All right. And so what we can do is, because it's a random sample, we can generalize to the population. In this case, the population is all dental patients, right? So we have a random sample of dental patients. We can generalize to all dental patients, okay? But again, because it's an observational study, we cannot make cause and effect conclusions, okay? We can only say that, sorry, what did I say? Okay. So we can generalize to all dental patients. We can't generalize to the entire town, okay, because we only got a random sample of dental patients, right? If we say the dental patients are representative of the entire town, then maybe that's okay, right? But each of these things, you're making an assumption about what your population looks like and what your sample looks like, okay? And again, we cannot make any kind of conclusion about why. Okay, and then the scenario 4 is we got a random sample and we did random assignment, okay? All right, and so this is both a random sample and an experiment, okay? And so we can, so with this, we can generalize to the population, okay? And we can make a cause and effect conclusion, okay? Because it's been an experiment, right? And so that's like the dream scenario, okay? But the truth is this scenario is like almost impossible in real life, okay? It's almost impossible to have both random sampling and a random experiment, okay? Because to do an experiment, you need consent of the person to participate in the experiment, okay? And not every, like, you might have gone through the trouble of identifying a random selection of people, okay? But if not 100% of the people consent to be part of the experiment, it's no longer a random sample, okay? And if your experiment has anything to do with, like, do you mistrust authority or something like that, right? Then the people who consent to be part of your experiment and the people who don't, might look different from each other. And so, in reality, it is, it's almost impossible. It's very rare to have both random sample and random assignment, okay? And so oftentimes, you are in a situation where your data was obtained via random sampling, or your data was obtained via random assignment in some kind of experiment, okay? And then how your data was obtained will have implications as far as what kind of conclusions you can make and what kind of statistical methods we can do, okay? And so, so next week, we'll take a look at randomization tests and bootstrap tests, and this will kind of cover hypothesis testing that doesn't rely on the t-distribution, but rather the sampling distribution that we can get from randomization or bootstrapping. Okay, so we'll take a look at that on Monday when you guys come back. With that, we'll have a good weekend, and we'll see you guys in a few days.